In this example, we're going to consider an optimization problem which has a constraint that is nonlinear. So it's going to be slightly more intricate in terms of the calculations, though the underlying ideas are the same. The idea here is to find the points on the curve, x to the 4, y to the 4 equals 1. And so that would be our constraint. And we notice that it looks an awful lot like a circle, but because we have powers to the 4 here, it's actually not quite a circle. We'll see a diagram or a contour diagram with this later on showing you the exact shape. But you can imagine there's symmetric elements to it. It's just not quite circular. So we consider all the points on that curve, so some kind of circle-ish type shape. We can walk all the way around it. And we want to find those that are closest to and furthest from the origin. So presumably you've got a nice axis set over here, and some points are going to be closer, others are going to be further. Well, to do our Lagrange multiplier process, to identify these special points that are closest and furthest from, we need to define a distance. If we want to know furthest or closest, we find the distance for any point and then identify the minima and maxima of that. Now, we've seen this trick before. We know the distance function for any 2 points has a nasty square root in it, but if we square everything, the closest point by distance squared will also be the same as the closest point by just regular distance, and that will make our life a lot easier, because that turns the distance function to simply x squared plus y squared. Any point from the origin will be distance xy away, then one axis and the other axis, and the hypotenuse squared will be x squared plus y squared. All right, with that in mind, we now have our ingredients. We have the function that we're trying to optimize, that we're trying to find the min and max of. We have our constraint up here, and in particular, we have the half of our constraint that we need, which is the functional part, x to the 4, y to the 4, and we're limiting ourselves to the value 1, but the constraint function we can think of, g of xy, is x to the 4, y to the 4. So, next step. Set up our Lagrange equations, and we'll do this directly. Here's our f of x, the thing we're trying to optimize. We need its x derivative, and that should equal some unknown scalar lambda times the x derivative of g, so 4x cubed. There we go. That's our x derivative of g, and likewise we take our function and we take the y derivative. Nice 2y here. Lambda y derivative of this is 4y cubed. F sub y. Oops. Lambda isn't in the derivative, it's just the second part here, g sub y. There we go. And we need a third equation because we have x, y, and lambda as our unknown. The last equation that we need is x to the 4 plus y to the 4 equals 1. And that is our set of 3 equations, 3 unknowns we need to solve to identify the closest and furthest points, or the maximum and minimum of our distance function, knowing that we can only walk along points that satisfy that constraint. Okay, so now our goal is to solve for x and y. The first equation here, let's give these numbers, 1, 2, and 3. The first equation gives us one answer really easily. If x was 0, this would be satisfied. So 1 gives us x equals 0, or if I factor that out or divide through that by x, I would have 2 equals lambda times 4x cubed, or 1, let's do it this way. Let's do it as lambda equals 1 over 2x squared. Take this equation, divide through by x, so that means x is 0, or we satisfy this equation. The second equation tells us that y could be 0, because if y is 0 on both sides, we're done, or that 2 is going to equal lambda times 4y squared, or lambda equals 1 over 2 y squared. That gives us those sets of constraints. And, well, we'd like to get these two together. So let's combine, let's call it 4 and 5 here. Both equal lambda. We can set both sides equal to each other. And we obtain 1 over 2x squared. 1 over 2x squared is going to equal 1 over 2y squared, or x squared equals y squared. And that can be more simply put as y equals plus x, or y equals negative x. If they're both equal to each other squared, then the y would equal the positive or negative version of x. And that gives us quite a collection. So x could equal 0, y could equal 0, or y could equal positive x, or y could equal negative x. So what do we do with all that? Let's bring it to the next page and see what we can derive from all of that information. If we let x equal 0, so that's one case. If x equals 0 and y equals minus x would be one temptation, that doesn't actually work because we have the third constraint we haven't actually used yet. It doesn't satisfy the constraint, which is conveniently written right here. So better to put this into the constraint equation, which is x to the 4 plus y to the 4 equals 1. If x is 0, then we get 0 plus y to the 4 equals 1. And so y is equal to, how can we take the fourth root here? We can get a plus 1 or a minus 1. Okay, so we use the x equals 0 value, we plug it into our constraint equation, the third equation, label that there, and we get two y values that go with that, and so we have 2 points. All right, not too bad. So we have 2 points that satisfy the Lagrange equations. We also have another case. We could have y equals 0, and we sub that into our constraint equation again, and we're going to get x to the 4 plus 0 equals 1, and from that, parallel to this other example, we could say that x is equal to 1 or negative 1. These are the x coordinates, so it could be 1 for x, or it could be negative 1 for x to go with y equals 0. And that's 2 more points. So we can already see we're getting a little more exotic in terms of our range of values. And we're still not done yet. The other constraint from the previous page involved y plus y equals x, or y equals negative x. So that's another set of explorations we have to make. Let's call it case 3, y equals x. If that's the case, our x to the 4 plus y to the 4 is our constraint, so we're putting it back into equation 3. We could have 2x to the 4s here equal 1, and that gives us 2x to the 4 equals 1, or x equals the fourth root of 1/2. And we started off this with the premise that y equals x, so that also equals y. And we notice because it's an even root, we could have the plus or the minus. So if our x is positive, the fourth root of 1/2, then our y would also be the positive fourth root of 1/2. And yet another case, the negative branch here is x equals negative fourth root of 1/2, and the y is equal to the x. That was our starting assumption for this case, and so we get a negative fourth root of 1/2. And we're still not done. All right, case 4. We're getting close though. We are getting close. Y equals negative x. When we sub that into our equation 3, the constraint, x to the 4 plus y to the 4, well, y is negative x, so let's write this out thoroughly here. We're going to get the fourth power of negative x, that's going to be positive. So we're going to end up again with 2x to the 4 is equal 1. And from there, x is going to equal plus or minus the 4th root of 1/2. And whatever we pick for x, y is going to equal negative x. So we'll have to flip some things here. So in fact, it'll be symmetric with what we found just in the last stage. If I choose the positive x value, the positive root, I'm going to get the negative y value. And we get a different point than the last time. If I take the negative x value, 4th root of 1/2, then we're going to get the positive root for y, 4th root of 1/2. And so in total, we have a whopping 8 points that satisfy our equations. Whew! All right, so let's regroup. Let's just quickly recap what we just did. We had a function that we wanted to optimize, distance to the origin squared. We had a constraint. We're only allowed to pick points that lie on this surface, or this curve rather, x to the 4 plus y to the 4 equals 1. To find the points where this function is maximized but still subject to this constraint, we use this constraint to set up our Lagrange equations with the function, and we ended up with several conditions. If any of these conditions were true, we'd have to go through, but we should have these equations satisfied. All of those cases led us down the road to 8 points, 8 xy coordinates that had that satisfy those original equations. Last but not least, we would like to know which points are mins and which are maxes. Well, remember that our function, which is the distance function, let's call it d for real here, d of xy is going to equal x squared plus y squared. That's our distance function squared. And so we evaluate at, they're sort of like critical points, but they're the interesting points that we just found on the last page, and we'll see what kind of function values we get. At the point 0, 1, we're going to get a distance squared of 1. At the point 0, negative 1, we're going to get a distance of 1. At 1, 0, we're going to get a distance of 1. At the point negative 1, 0, we're going to have a distance squared of 1. Those are nice. We can work with those. All right. The other points we might be interested in, that we are interested in, are all of these 4th roots of 1/2. And one of them was both positive, and that led to a distance of 4th root squared gives me a square root. So square root of 2 plus square root of 2, that's going to be, square root of 1/2, square root of 1/2, let's be precise here, is going to equal 2 square roots of 1/2. You can leave it like that if you like, or you can actually bring this in as the square root of 4 over 2, so it's actually just root 2. Okay, and then we have the mix and match, 4th of 1/2 and the negative 4th root of 1/2. The distance squared we get with that will be exactly the same. We're going to square the first one, that'll take care of the negative, so we're going to have this regular square root of 1/2. And we're going to square this, again, get rid of the negative. We're going to square root of 1/2, and we just showed that's root 2. And I think we see a trend happening here. So if we take the negative, same thing and the same thing, or the same thing and the negative for y, d is going to be root 2, d is going to be root 2. Okay, what does that tell us? These are the distances squared to the origin. These points have the same, and let's be clear here, this number is bigger than 1, larger distance to the origin. And so these would be the furthest on x to the 4th plus y to the 4th equals 1. That's our constraint. These ones have the smallest distance to the origin. And so that means that they would be the points that are closest to the origin if we consider only those points on x to the 4 plus y to the 4 equals 1. And that completes the analysis, simply by comparing the function values at these 8 points here with a lot of symmetry. We've identified that these coordinates here will be the furthest of the points that satisfy this equation, and these will be the closest. Now it really does help to look at this geometrically. This curve here is the graph of x to the 4th plus y to the 4th equals 1. So we can pick any point we like along this ring. Notice it's circular, it has some symmetry to it, but it's not actually a circle. It's actually a rounded off square or a squared off circle, whichever way you want to think of it. And we can pick any point along here that we like. What we have here are the contours of the distance squared. And if that's what we have here, well, we want to, obviously if we want to get close to the center, we should move as far towards the middle as we can. If we want to move and get further from the origin, we should move far out from the center. Let's overlay those two. So combine this graph and that graph. As we go around the black line, we see different scenarios happening. As we come along here, we see that, the red line and the black line intersect. But when we hit just this corner here, we see that we've pushed out as far as we can. We can see this red line here, we're just tangent to it. That's the furthest point we can reach. And where does that point happen to be? It happens to be at the 4th root of 2, or sorry, 4th root of a half, negative because we're to the left of the origin, and the y-coordinate though is the positive 4th root of a half. That would be a point on this black line. It satisfies the constraint, and it's also the point that's furthest away. And not surprisingly, it has 3 other friends that are also the same distance away, and it's all the combinations plus or minus for the x and y's, this 4th root of a half. What about the other 4 points? We also said that 0, 1, so right here, and negative 1, 0, that's negative 1, 0, 0, negative 1, 0, 1, were the closest points. And guess where those are? The ones that we found algebraically. Let's do them in the same order. And 0, negative 1, and negative 1, 0. Those 4 points we can see are the closest. And again, if we look at points as we move along the constraint, along the contour black line here, we're getting towards this lowest contour, this red line, getting closer and closer until we just touch it, and then we start moving away and moving further away from the origin. So those 4 points there are the closest to the origin, and they also happen to be tangent to the contour, the lowest height that we can reach while walking along this path. So this is a quite involved example, but all the elements of a classic Lagrange constraint optimization problem are shown here.